The universe is full of secret structures so strange and vast they make galaxies look like tiny specks of dust. But here's the thing, everything we think we know about space might just be the tip of the iceberg. What if the cosmos hides layers of reality we can't even perceive? Some theories suggest the fabric of existence is woven with invisible threads, dimensions folded like origami, and forces beyond anything science has named. Today, we're peeling back the curtain to reveal 30 mind-bending ideas about these hidden cosmic blueprints theories that could rewrite everything from gravity to the nature of time itself. And trust me, by the end, you'll never look at the night sky the same way again. What if everything you see, the stars, the planets, even your own hands, wasn't truly three-dimensional at all? This is the startling claim behind the holographic principle, one of the most radical ideas in modern physics. The theory suggests that the universe we experience might actually be a vast, intricate projection like a cosmic hologram encoded on a distant two-dimensional surface. It sounds like science fiction, but the roots of this idea trace back to one of nature's most mysterious phenomena, black holes. In the 1970s, physicist Jacob Bekenstein discovered something bizarre about black holes. Their entropy, or hidden information, doesn't depend on their volume but on their surface area. Later, scientists like Gerard T. Hooft and Leonard Susskind expanded on this, proposing that the information inside a black hole isn't lost but stored on its event horizon, the point of no return. If that's true, could the same logic apply to the entire universe? Imagine the cosmos like a movie screen. Every explosion, every galaxy, every sway of a tree branch might just be data painted onto the edges of reality, flickering into three dimensions like a hologram brought to life. If confirmed, this would mean that space itself is an illusion, a construct built from deeper, invisible laws we're only beginning to grasp. Skeptics argue it's too strange to be real, but experiments with quantum gravity and particle physics keep hinting that reality might be far weirder than we ever thought. So the next time you gaze up at the night sky, ask yourself, are we truly in space, or are we just watching it from a cosmic boundary we can't even see? Now picture the universe not as a smooth, seamless fabric, but as one riddled with flaws, tiny, unimaginably dense cracks threading through spacetime itself. These are cosmic strings, theoretical relics from the earliest moments of creation, thinner than an atom yet massive enough to warp the cosmos around them like invisible wires cutting through reality. Born in the chaos of the Big Bang, cosmic strings could be the universe's scars, remnants of phase transitions so violent they left defects frozen into the structure of spacetime. Think of it like ice forming on a pond. As water cools, cracks and imperfections emerge. In the same way as the young universe expanded and cooled, spacetime itself might have fractured, leaving behind these bizarre, one-dimensional cracks. But here's where it gets wild. If they exist, cosmic strings wouldn't just sit there, they'd pull. Their immense mass would distort space around them, bending light like a funhouse mirror, a phenomenon called gravitational lensing. Some scientists even suggest these strings could have acted as cosmic scaffolding, guiding the formation of galaxies along their tangled paths. And because they vibrate at near-light speeds, they might ripple spacetime itself, sending out gravitational waves we could detect. The best evidence for cosmic strings, faint, ghostly imprints they'd leave on the cosmic microwave background, the afterglow of the Big Bang. Like shadows cast by invisible threads, these anomalies could reveal where spacetime itself is subtly torn. So far, no definitive string has been found, but if we ever spot one, it wouldn't just be a discovery. It'd be a glimpse into the universe's raw, imperfect beginnings, proof that even emptiness has a texture. What if our universe isn't alone, but just one page in an endless cosmic library, where every possible version of reality exists simultaneously? This isn't science fiction, it's the level I multiverse, a staggering prediction of inflationary cosmology that suggests spacetime stretches far beyond what we'll ever observe. And here's the jaw-dropping part. If the universe is infinite, every configuration of matter, every twist of physics, even alternate versions of you, must exist somewhere out there. The idea springs from a simple but profound observation. If the Big Bang sent space expanding faster than light, a process called inflation, then regions of the universe too distant for us to see could host their own bubble universes, each with unique physics. Picture blowing soap bubbles in a never-ending foam. Each bubble is a self-contained cosmos, isolated from the others, yet born from the same explosive beginning. In some, gravity might be stronger, in others, stars might never form. And statistically, given enough space, every possible arrangement of particles must repeat. But how could we ever test something so vast? The clues lie in the cosmic microwave background. If another universe's gravity leaked into ours, it might leave faint imprints, like cosmic fingerprints on this ancient radiation. Some physicists even speculate that a collision between bubble universes could have left a bruise on the fabric of our sky. Skeptics argue this is untestable philosophy, not science. Yet supporters counter that inflation demands this conclusion. If space is infinite, the multiverse isn't optional but inevitable. So the next time you feel déjà vu, wonder, somewhere in another cosmic bubble, another version of you might be pausing too, staring at their own night sky, asking the same questions. Somewhere beyond the edges of our observable universe, entire realities might be bubbling into existence, each one operating under completely different rules. This isn't just about infinite copies of our cosmos, like in the level I multiverse. This is the level Roman II multiverse, where universes aren't merely distant. They're fundamentally alien, with unique physics, forces, and even dimensions. And the driving force behind this cosmic proliferation, eternal inflation. Here's how it works. Moments after the Big Bang, space didn't just expand. It exploded outward at breakneck speed, a process called inflation. Most theories assume this eventually stopped, giving rise to our stable universe. But some physicists, like Alexander Vilenkin, argue inflation never truly ends. Instead, it keeps stretching the fabric of spacetime infinitely, with bubble universes pinching off like droplets in a boiling ocean. Inside each bubble, the laws of physics could have settled differently. One might have stronger nuclear forces, making stars burn out in seconds. Another might have extra-spatial dimensions, with matter behaving in ways we can't even visualize. The key contrast with the level I multiverse. There, infinite space guarantees all possible arrangements of matter repeat, but the fundamental physics stays the same. Here, the rules themselves change from bubble to bubble. Some universes might collapse instantly, others could be ruled by chaos, never forming atoms at all. Ours, with its delicate balance allowing for life, might be a rare fluke in a sea of unstable experiments. So where's the proof? That's the catch. Unlike level I, where collisions with other universes might leave scars in the cosmic microwave background, level Roman II bubbles are forever cut off from us by the relentless expansion of space. We can't see them, touch them, or even detect their influence. Critics argue this makes the idea untestable, more metaphysics than science. But supporters counter that eternal inflation is the most natural extension of our best theories. If true, it means reality isn't just vast, it's varied, a cosmic lab where universes rise and fall with their own unique blueprints. The takeaway: if level Roman II is real, our universe isn't special, just one accidental recipe in an endless cookbook of physics, where most pages are scribbled with laws too extreme for life. And that raises a haunting question. In this sea of possibilities, are we the rule or the exception? Imagine a moment where you had to make a choice, maybe turning left instead of right, or speaking up instead of staying silent. Now picture this: what if both outcomes happened, not just in your mind, but in reality, splitting the universe into two separate timelines? This isn't just a thought experiment, it's the many worlds interpretation, or level Roman III multiverse, a radical vision of reality where every quantum possibility plays out in its own branching universe. Proposed by physicist Hugh Everett in the 1950s, this theory tackles one of quantum mechanics' biggest mysteries: why particles seem to exist in multiple states until observed. The classic example is Schrödinger's cat, a thought experiment where a cat in a box is both alive and dead until someone looks, but Everett's solution flips the script. There's no single collapse into one outcome. Instead, both happen, each in a newly spawned universe. Miss a bus, one version of you sighs on the sidewalk, another catches it and arrives on time. Every flicker of a particle, every neural spark in your brain could be writing infinite parallel stories. The implications are dizzying. If many worlds is true, then somewhere every historical what-if is real. A universe where dinosaurs never went extinct, one where you became an astronaut, even worlds where the laws of physics differ slightly just by chance. Unlike the Level I and Roman II multiverses, where universes are separate bubbles in space, here they're stacked like pages in a book, all existing right now but forever out of reach. Critics argue it's untestable. How do you prove the existence of universes you can't interact with? Yet supporters counter that it's the simplest explanation for quantum weirdness, stripping away the need for mysterious collapses or observers. And philosophically, it forces a humbling question. If every possibility happens, does choice even matter? But here's the twist. If parallel views are constantly diverging, they might not stay strangers forever. Some versions of the theory suggest quantum vibrations could leak between worlds, creating faint echoes like déjà vu, or dreams of lives you never lived. Wild, absolutely, but in a reality where particles teleport and black holes erase information, perhaps the most shocking idea is that our intuition ever made sense to begin with. We've explored bubble universes and branching timelines, but what if every mathematically possible reality isn't just theoretical but actual? This is the audacious claim of the mathematical universe hypothesis, or level Roman IV multiverse, where numbers don't just describe the cosmos, they are the cosmos. Forget fine-tuned physics or quantum splits. Here, any structure that can exist in equations must exist somewhere in the grand ensemble of reality. And that includes universes so bizarre, even our wildest sci-fi couldn't imagine them. The idea comes from physicist Max Tegmark, who argues that abstract mathematics isn't merely a human invention for decoding nature, it's nature's bedrock. Picture a cosmic catalog where every consistent mathematical structure, from the familiar laws of our universe to alien geometries with 26 dimensions, physically manifests as its own standalone universe. In this view, our universe isn't special because it permits life. It's simply one page in an infinite textbook of self-consistent equations, a cosmos where gravity repels. Exists, one made entirely of fractal patterns, exists, even realities where time runs backward or causality loops like a Möbius strip would be out there, not as hypotheticals but as concrete places. But how could we ever test something so abstract? That's the elephant in the room. Unlike other multiverse levels where collisions or quantum echoes might leave traces, level Roman IV offers no obvious bridges between mathematical structures. Tegmark suggests one clue. If our universe's fundamental constants had to take their values for mathematical consistency, not just random chance, that could hint at a deeper, number-driven reality. Others propose that advanced civilizations might one day manipulate pure math to communicate across these platonic realms, though that ventures deep into speculation. Critics push back hard, calling level Roman IV less science than metaphysics. If a theory can't make falsifiable predictions, is it even physics? Yet supporters counter that dismissing all untestable ideas risks blinding us to truths beyond current tools. After all, black holes and quantum entanglement once seemed equally outlandish. Here's the mind bender: if Tegmark's right, then Pythagoras was onto something. Cosmic reality isn't just written in the language of math. It is math, and that means every time you solve an equation, you might not just be doing homework but glimpsing another universe. For decades, astronomers assumed the cosmos expanded uniformly in all directions, a grand, balanced dance of galaxies drifting apart. But then came dark flow, an eerie discovery that shattered this simple picture. Observations revealed something impossible. Hundreds of galaxy clusters, each weighing a quadrillion suns, racing toward the same distant void faster than the universe's expansion should allow. It's as if space itself has a riptide, dragging everything toward a hidden horizon we can't see. The first clues emerged in 2008 when NASA Wilkinson microwave anisotropy probe studied the cosmic microwave background, the afterglow of the Big Bang. Scientists expected tiny temperature fluctuations, remnants of ancient density variations. Instead, they found something stranger, a pattern suggesting galaxy clusters were all being tugged in the same direction, like iron filings drawn to a magnet outside our field of vision. Follow-up studies confirmed it. These clusters weren't just moving, they were aligned, streaming toward a point roughly 3 billion light-years beyond the edge of the observable universe. So what's pulling them? One explosive possibility: other universes. In certain multiverse models, like those arising from eternal inflation, neighboring bubble universes could exert gravitational influence on ours. Picture a cosmic game of tug-of-war, where an immense structure in another reality, perhaps a supermassive black hole or a dense knot of dark matter, warps spacetime enough to create this mysterious flow. Alternatively, dark flow might trace back to irregularities in the very early universe, scars from a time before inflation smoothed everything out. Skeptics argue it could just be a measurement error or a local anomaly. But the scale is undeniable. This isn't a handful of galaxies wobbling. It's a continent-wide current in the ocean of space with no visible source. If future telescopes detect the same motion in even more distant clusters, the implications would be staggering. Evidence that our universe isn't isolated, but nudged by something vast and unseen. Dark flow doesn't just challenge our maps of the cosmos. It hints that the greatest structures in existence might lie just out of frame, their gravity reaching across the void to steer everything we know. And that raises a chilling question. If the universe is pulling us somewhere, what's waiting at the other end? Picture this: instead of a single explosive beginning, the universe might be locked in an eternal dance, expanding, contracting, and reborn in an endless cycle of cosmic resurrection. This is the Big Bounce, a radical alternative to the Big Bang that suggests our universe isn't the first and won't be the last. Here's the twist: while the Big Bang paints the cosmos as a one-time event, the Big Bounce proposes that every collapse becomes a rebirth. Imagine a cosmic lung, inhaling as galaxies rush inward under gravity's pull, reaching a point so dense and hot that quantum physics takes over. Then, exhaling with a rebound, space exploding outward again in a new fiery dawn. No singularity, no nothingness before, just an infinite loop of universes breathing in and out. But there's a catch. Physics tells us entropy, the slow march toward disorder, always increases. If each cycle inherited the chaos of the last, wouldn't the universe grow more disordered with every bounce? Eventually, it'd be too scrambled to form stars or planets. Supporters of the theory, like physicist Paul Steinhardt, argue quantum gravity effects near the bounce could reset entropy, wiping the cosmic slate clean. Others suggest dark energy, the mysterious force accelerating expansion, might evolve over cycles, ensuring each new universe gets a fresh start. Critics aren't convinced. Without proof of entropy resetting or quantum gravity's exact rules, the Big Bounce remains speculative, yet tantalizing clues linger. If previous cycles existed, they might have left faint imprints in the cosmic microwave background, subtle swirls or anomalies that telescopes could one day detect. And if space ever stops accelerating outward, gravity could begin pulling everything back toward the next bounce, though that fate, if it happens, is trillions of years away. What's captivating about this idea isn't just the science, it's the poetry. A universe without true death, where endings seed beginnings. If true, the night sky isn't just a static relic of one explosion, but a single frame in an infinite cosmic film, replaying with variations we'll never live to see. So the next time you hear about the Big Bang, ask, what if it was just the latest echo in a chain of universes stretching forever backward and forward? The universe isn't just expanding. It might have been born from a collision in a hidden dimension, like a cosmic car crash echoing through reality. This is the ekpyrotic universe theory, a bold twist on cosmic origins where the Big Bang wasn't a singular explosion, but the aftermath of two immense floating membranes called brains smashing together in a higher dimensional space. The idea springs from string theory, which suggests particles aren't just dots but tiny vibrating strings. To make the math work, string theory requires extra dimensions, up to 10 or 11, curled up so tightly we'll never perceive them. And within these hidden layers, enormous brains short for membranes could exist, stretching across dimensions like vast sheets of spacetime. In the ekpyrotic scenario, our entire universe is just one of these brains, and it all began when a neighboring brain, drifting through the higher dimensional void, collided with ours. Picture two slices of bread floating in a cosmic loaf, slowly grazing each other. The energy of their impact wouldn't just make a sound, it'd ignite a firestorm of matter, radiation, and expansion, birthing the universe as we know it. Unlike inflation theory, where space ballooned from a single point, here the Big Bang was more like a shockwave rippling across our brain's surface. Supporters love this model's elegance. It explains the universe's smoothness without requiring hyper-fast inflation. Instead, the brains could have stretched flat over eons before colliding, smoothing wrinkles naturally. Even the cosmic microwave background's temperature patterns, mysterious in standard models, might just be bruises from the crash. But skeptics point to gaps. If brains exist, why can't we detect higher dimensions, and how often do these collisions happen? Some versions of the theory suggest cycles, brains eternally ricocheting apart and crashing back, while others imply a one-time event lost to prehistory. The wildest implication, if true, another brain might still hover just beyond our dimensional reach, invisible yet closer than anything in our 3D world. One speculative twist: dark matter could be particles stuck to our brain's surface, while dark energy is the tension of spacetime itself, still recoiling from that ancient collision. So forget fireworks, our origin story might be more like an earthquake in the hidden architecture of reality, a tremor we're still riding 14 billion years later. And if brains are real, the next cosmic dawn could already be looming in dimensions we'll never see. What if the universe didn't just form naturally, but was deliberately built? This is the core of the simulation argument, a theory that suggests reality as we know it could be an artificial construct, an ultra-advanced simulation running on some unfathomable computer. And it's not just the stuff of sci-fi. Philosophers, physicists, and tech billionaires have all wrestled with its startling implications. The idea traces back to legends like Plato's allegory of the cave, where humans mistake shadows for reality. But the modern version gained traction in 2003, when philosopher Nick Bostrom laid out a chillingly logical case. If civilizations ever reach the technological capacity to create conscious simulations indistinguishable from reality, and if they choose to run them, then the odds say we're far more likely to be in one of those simulations than in the original universe. Think of it like this: if future humans run billions of ancestor simulations, the sheer math suggests this: your life, your memories is probably one of them. But where's the evidence? Some theorists point to potential glitches in reality, tiny, unexplained anomalies that could hint at underlying code. Ever experienced déjà vu or seen quantum particles behave differently when observed? These could be artifacts of computational shortcuts, like a game simplifying graphics when no one's looking. Others suggest the very precision of physical constants, gravity's strength. The speed of light smacks of deliberate tuning, as if a programmer tweaked the settings to allow for stars, planets, and life. Not everyone's convinced. Physicists like Neil deGrasse Tyson counter that glitches might just be gaps in our current knowledge, not proof of simulation. And then there's the simulation paradox. If we're simulated, wouldn't our creators also likely be simulations, nesting endlessly? Still, some scientists propose wild ways to test the idea, like hunting for pixelation in high-energy cosmic rays or exploiting quantum oddities to hack the system. Here's the twist: the simulation argument isn't really about aliens or machines. It's about the nature of reality itself, whether existence is fundamental or just another layer in an infinite stack of illusions. If true, it wouldn't make life meaningless, it'd make curiosity our greatest weapon. After all, what's more human than poking at the edges of the universe, wondering if there's an off switch? What if the entire universe, every star, every galaxy, even time itself wasn't born from nothing, but spilled out from the wreckage of a cosmic monster? This is the black hole universe theory, a mind-bending idea proposing that our reality might be the interior of a black hole in a vastly larger parent cosmos. And the eerie similarities between black hole physics and the Big Bang suggest this isn't just poetic speculation, it could be woven into the fabric of existence itself. Let's break it down. At the heart of a black hole lies a singularity, a point of infinite density where space and time break down. But here's the twist: our own Big Bang also began with a singularity. Both represent moments where the rules of physics collapse, where matter, energy, and even causality lose meaning. So could they be the same phenomenon, just viewed from different angles? Some physicists, like Nikodem Poplawski, argue that when a black hole forms in the parent universe, its crushing gravity doesn't just trap matter, it rebounds, triggering a new expansion, a Big Bang from the inside. Think of it like a cosmic Russian nesting doll. Our universe's expansion isn't an explosion into empty space, but the stretched fabric of a black hole's interior, forever growing as new matter falls into the parent hole's event horizon. This would also explain why our universe seems so finely tuned for complexity. Only black holes with the right conditions, specific spins, charges, or masses could birth stable universes inside them. Fail those checks and the new reality might collapse instantly or stretch into barren emptiness. Supporters point to puzzling clues. Black holes emit radiation and eventually evaporate, but where does their information go? If each hole contains a universe, that data might be preserved in the new cosmos structure. Even dark energy, the mysterious force accelerating expansion, could be the gravitational echo of the parent black hole's pull. Of course, skeptics highlight the gaps. How would we ever observe the outside universe? If true, this theory might forever remain untestable, a haunting maybe at the edge of science. Yet the elegance is undeniable. A universe where black holes aren't just tombs, but cosmic wombs passing the torch of existence from one reality to the next. So the next time you hear about a black hole devouring a star, consider this: somewhere in a realm beyond time, that destruction might be lighting the fuse of an entirely new cosmos. And if that's true, our entire existence could be the aftermath of someone else's collapse, a phoenix universe, rising from the ashes of a forgotten giant. Theory 12. The axis of evil. Science thrives on patterns, except when those patterns defy all expectations. That's the unsettling mystery behind the so-called axis of evil, a bizarre alignment in the cosmic microwave background that seems to point directly at our solar system. It's as if the universe left a fingerprint and it's facing us. Discovered in 2005 by researchers studying the Planck satellite's data, the anomaly shows something eerie. Temperature fluctuations in the ancient afterglow of the Big Bang aren't entirely random. Instead, they appear weakly aligned along a specific axis, one that suspiciously lines up with the plane of our solar system. The odds of this happening by pure chance? Astronomers estimate less than 1 in 100. So what's going on? One camp argues it's a fluke, an artifact of measurement errors or incomplete data. After all, the cosmic microwave background is incredibly faint, and Earth's motion through space could subtly distort what we see. But others whisper about more radical possibilities. Could this axis hint at a preferred direction in the universe, violating the sacred cosmological principle that space should look the same in all directions? Or worse, is it evidence that our corner of reality is somehow special, despite centuries of scientific insistence that we're not? Supporters of new physics suggest exotic explanations. Maybe the early universe spun like a top, imprinting a primordial axis on spacetime. Or perhaps dark energy isn't uniform but flows along invisible cosmic currents. The wildest idea, that we're seeing the gravitational shadow of a neighboring universe tugging on ours from beyond the observable horizon. But here's the twist: if the axis of evil is real, it wouldn't just rewrite textbooks, it'd force us to question whether we've misunderstood the universe's structure from the start. For now, the debate rages on, with newer telescopes like the Euclid mission searching for answers. Until then, this eerie alignment remains a cosmic riddle, whispering that the universe might not be as indifferent to us as we once thought. Theory 13. The Great Attractor. Something out there is pulling us, not metaphorically but literally. Across the cosmos, galaxies, including our own Milky Way, are streaming toward a mysterious gravitational force so immense it defies explanation. Astronomers call it the Great Attractor, an unseen heavyweight lurking in the shadows of space, tugging on everything within hundreds of millions of light years. And the strangest part, we can't even see what's causing it. This cosmic mystery hides in the zone of avoidance, a region of the sky obscured by the dense dust and stars of our galaxy's disk. It's like trying to spot a mountain behind a thick fog, except this mountain has the mass of tens of thousands of Milky Ways. Early hints emerged in the 1970s when astronomers noticed galaxies in our local supercluster drifting toward the same invisible point. Their speeds didn't match the universe's overall expansion. Something massive was warping space, bending their paths like a hidden magnet beneath a sheet of paper. So what is it? One leading theory points to the Norma supercluster, a dense knot of galaxies and dark matter in the attractor's rough direction. But estimates suggest even that isn't heavy enough to explain the pull. Could there be something larger lurking behind it, an ultra-massive structure we've yet to map? Others propose the attractor might be a remnant of an ancient cosmic collision, where multiple galaxy clusters merged into a gravitational titan. But the plot thickens. Recent observations reveal the Great Attractor itself might be just a waypoint, a stepping stone in an even grander cosmic current. Beyond it lies the Shapley supercluster, the most massive concentration of matter in our observable universe, pulling the attractor, and us, toward it like a waterfall's inevitable drop. The irony is palpable. In a universe where dark energy pushes everything apart, local physics still dances to gravity's tune. And until telescopes peer deeper into the zone of avoidance, the Great Attractor remains a ghost in the machine, a reminder that even in the vastness of space, some forces refuse to stay hidden. So the next time you look toward the constellation Centaurus, remember, out there in the dark, an invisible hand is guiding our galaxy's journey. The only question left is, what's waiting at the other end? Theory 14. The void hypothesis. Picture standing in the middle of an empty stadium, no crowd, no noise, just vast, echoing space stretching in every direction. Now scale that up to cosmic proportions, and you've got the essence of the void hypothesis. A radical idea suggesting we might be floating inside a colossal, near-empty bubble in the universe. And this isn't just about emptiness. It could rewrite our understanding of dark energy, the mysterious force accelerating the cosmos apart. Here's the puzzle. For decades, astronomers assumed space was roughly uniform on large scales, a principle called cosmic homogeneity. But if we happen to reside in an unusually sparse region, a void spanning billions of light years, the lack of surrounding matter could distort our measurements of cosmic expansion. Gravity from denser regions outside the void would tug matter inward, making it seem like an unknown force, dark energy, is pushing everything apart faster than expected. In other words, dark energy might not be a fundamental force at all, just a cosmic illusion caused by our unlucky real estate. The standard model of cosmology, known as lambdactum, treats dark energy as a constant woven into the fabric of spacetime itself. But the void hypothesis offers a provocative alternative. No exotic energy, just a giant structural oddity tricking our instruments. Supporters point to peculiar observations, like certain supernova appearing dimmer, and thus farther away than lambdactum predicts exactly what you'd expect if we're in a low-density zone where space expands faster locally. Even the cosmic microwave background's temperature fluctuations show slight anomalies that could hint at a void's gravitational influence. Critics fire back with two big challenges. First, a void large enough to mimic dark energy would defy the odds, making our position absurdly special, a direct contradiction to cosmology's Copernican principle. Second, galaxy surveys suggest matter is distributed fairly evenly across the universe, with no gaps vast enough to explain the effect. Yet intriguingly, some studies have identified a curious cold spot in the cosmic microwave background, a potential fingerprint of a supervoid shadow. If the void hypothesis holds water, the implications would be staggering. It wouldn't just mean dark energy is a mirage, it'd force us to reconsider whether the universe is as uniform as we thought. Are we cosmic outliers, or is the void itself part of a larger, frothy structure we've yet to map? For now, the debate rages, with next-generation telescopes like the Vera Rubin Observatory poised to scan deeper into the cosmic web. Either way, the lesson is humbling. Sometimes the universe's greatest mysteries aren't about what's out there, but where we are in the grand scheme of things. Theory 15. The time crystal universe. We think of time as an arrow always moving forward in a straight, unbroken line. But what if the universe has a hidden rhythm, a structure that repeats in time like the fractals of a snowflake? This is the wild promise of the time crystal universe, a theory where reality itself might be locked in an eternal dance of self-repeating patterns. The idea comes from an unexpected place, cutting-edge quantum labs. In 2016, physicists created the first confirmed time crystals, exotic phases of matter that don't just sit still, but pulse in regular cycles without any energy input. Unlike normal crystals where atoms arrange in repeating spatial patterns, time crystals repeat their structure in time, flipping between states like a clock ticking forever without winding. Now, some theorists wonder, could the entire universe operate on similar principles? Imagine cosmic history not as a linear march, but as a grand fugue, a composition where certain events, conditions, or even whole epochs echo at intervals across the lifespan of reality. Black holes might form in predictable cycles, vacuum energy could reset itself, or the laws of physics might subtly shift and then return like a cosmic pendulum. This wouldn't mean exact repetition, more like variations on a theme, where the universe explores every possible permutation of its own rules before circling back. Critics argue the leap from lab-scale time crystals to cosmology is vast, yet supporters highlight eerie clues. The universe's large-scale structure resembles a fractal, with galaxies clustering in self-similar patterns. Even the cosmic microwave background shows faint, repeating fluctuations that could hint at deeper temporal symmetry. If true, it would mean time isn't just a stage for events, it's an active participant, shaping reality from within. Here's the kicker: if the cosmos is a time crystal, the Big Bang might not be a one-time event, but a single note in an endless melody, and that changes everything, from how we view entropy to whether the universe has an expiration date. After all, if time can crystallize, who's to say eternity isn't built into the fabric of existence? No beginnings, no endings, just the universe forever finding new ways to rhyme with itself. Theory 16. The phantom dark energy model. Most forces in the universe fade with distance. Gravity weakens, light dims, but dark energy doesn't play by those rules. Instead of dissipating, it might be growing stronger over time, stretching spacetime until reality itself is torn apart at the seams. This nightmare scenario is the phantom dark energy model, and if it's real, the cosmos could be heading toward a fate more violent than anyone imagined: the Big Rip. Here's the unsettling part. For decades, scientists thought dark energy, the mysterious force accelerating cosmic expansion, was constant, represented by Einstein's cosmological constant. But what if it isn't? Phantom energy takes things further, suggesting dark energy amplifies as space expands, creating a runaway feedback loop. Picture blowing up a balloon that stretches faster the bigger it gets until the rubber can't take it anymore. Pop. Only in this case, the balloon is all of existence, and the pop shreds galaxies, stars, and even atoms into disconnected specks. The math is chilling. If phantom energy's strength crosses a critical threshold, it could overwhelm gravity's glue, dismantling galaxy clusters first. Next, stars would drift from their orbits, then planets from their suns. In the final moments, even atomic nuclei, the last structure holding matter together, would be ripped apart. Time itself might lose meaning in a state of infinite expansion. But not all dark energy models lead to doom. Some, like quintessence, propose it could weaken or fluctuate, leaving cosmic structures intact. Observations of distant supernova and galaxy clustering aim to track how dark energy's influence has changed over billions of years. So far, the data leans toward a constant cosmological constant, but with margins of error just wide enough to keep phantom energy on the table. Critics argue that phantom energy defies thermodynamics, potentially violating energy conservation. Yet supporters counter that in an accelerating universe, even the most intuitive laws might bend. The key test, pinpointing whether expansion is speeding up faster than expected, a smoking gun for phantom energy's exponential growth. Upcoming telescopes like the Euclid mission could settle the debate by measuring dark energy's footprint with unprecedented precision. One haunting implication: if phantom energy is real, the Big Rip might not be billions of years away. Some estimates place it within tens of billions, a blink on cosmic scales. So whether it's a future certainty or just a mathematical ghost, this model forces us to confront an uncomfortable truth. The universe's ending might not be a slow fade, but a violent crescendo with no encore. Theory 17. The mirror universe. Somewhere beyond our perception, an entire reality might be unfolding in reverse, where time flows backward, atoms spin the opposite way, and even your reflection could be a living, breathing version of itself. This isn't just a sci-fi trope. It's the mirror universe hypothesis, a startling prediction of fundamental physics that suggests our cosmos may have a hidden twin, perfectly symmetrical yet utterly alien. The idea springs from something called CPT symmetry, one of the most sacred rules in physics. CPT stands for charge parity and time, three fundamental properties that, according to theory, should always balance out. If you flip a particle's charge, turning matter into antimatter, mirror its spatial coordinates like a reflection, and reverse time's arrow, the laws of physics should hold true. Nature, in other words, seems to demand a perfect counterbalance to our universe. So where is it? Some physicists, like Nobel laureate Sheldon Glashow, suggest the answer might be hiding in plain sight. A parallel cosmos born alongside ours in the Big Bang, but governed by flipped physics. In this mirror realm, stars could burn with antimatter, time might rewind from our perspective, and even life could exist just built from atoms that spin the wrong way. And here's the kicker: this mirrored reality wouldn't just be theoretical. It might explain one of cosmology's biggest headaches, dark matter. If mirror particles exist, they'd barely interact with our world, passing through ordinary matter like ghosts. That's eerily similar to how dark matter behaves, invisible, yet detectable by its gravitational grip on galaxies. A mirror universe would naturally produce such shadowy matter, woven into the fabric of existence from the very beginning. But how could we ever detect something so detached from our reality? The answer might lie in the very edges of physics: neutrinos, those elusive particles that barely interact with anything. Some experiments, like the proposed Ptolemy project, aim to catch signs of hypothetical, sterile neutrinos, which could be whispers from the mirror universe leaking through. Even slight imbalances in cosmic ray particles might betray a hidden symmetry breaking between the two realities. Skeptics argue that without direct proof, the mirror universe remains a tantalizing what if. Yet its elegance is undeniable, a cosmos where every action here has an equal and opposite reaction there, not just in space but in time itself. Maybe that's why the universe feels so finely tuned, because it's literally balanced by its own reflection. So the next time you catch your mirror image blinking just out of sync, consider this. Somewhere beyond the glass, another version of reality might be reaching back. Theory 18. The information paradox solution. Stephen Hawking left us with a cosmic riddle that still haunts physics. When black holes evaporate, does the information they swallow vanish forever? That would shatter quantum mechanics' golden rule: information can never be truly destroyed. But if it escapes, how? Some of the boldest ideas in science now suggest spacetime itself might be the answer, rewriting our understanding of reality in the process. Take the firewall paradox. Imagine falling toward a black hole's event horizon, expecting the smooth, empty space Einstein predicted. Instead, you hit a searing wall of high-energy particles, a cosmic kill switch triggered by quantum mechanics trying to preserve information. Proposed in 2012, firewalls suggest that instead of information leaking back via Hawking radiation, it burns up at the horizon in a violent release of energy. But here's the catch: this violates relativity's prediction that free-falling observers should notice nothing unusual at the horizon. Physics can't have both, so which law breaks? Then there's ER equals EPR, a jaw-dropping idea from luminaries like Juan Maldacena and Leonard Susskind. The name is a mashup of two seemingly unrelated concepts: Einstein-Rosen bridges, wormholes, and quantum entanglement, EPR paradox. The theory proposes that entangled particles, those spooky action at a distance pairs, might be connected by microscopic wormholes threading spacetime's fabric. For black holes, this could mean information doesn't vanish or burn. It's transferred through hidden tunnels in the universe's architecture. The implications are staggering. If ER equals EPR holds, then black holes aren't information shredders but cosmic teleporters, with entanglement literally weaving the fabric of spacetime itself. It'd mean the quantum realm and gravity, physics' most stubbornly separate forces, are two sides of the same coin. Skeptics argue the math isn't yet testable, but supporters counter that experiments with quantum entangled systems might one day reveal traces of these spacetime stitchings. Here's the kicker: both solutions force us to rethink reality's foundations. Is spacetime a stage where events play out, or a dynamic network built from quantum links? The answer could redefine not just black holes but the very nature of existence, and that's the paradox's true gift. It doesn't just threaten physics, it pushes it somewhere entirely new. So next time you hear about a black hole's dark appetite, remember, the real mystery isn't what falls in, it's how the universe conspires to keep its secrets alive. Theory 19. The causal set theory. What if spacetime isn't smooth and flowing like a river, but stitched together from tiny, indivisible fragments, like pixels on a cosmic screen? That's the radical vision of causal set theory, a model where the universe isn't a seamless continuum but a vast network of discrete, interconnected moments. Forget the traditional image of space and time as a stage. Here, reality is built from something far stranger, events linked by cause and effect in a shimmering web of relationships. At the heart of this idea is a simple but profound shift. Instead of treating spacetime as fundamental, causal sets propose it emerges from something deeper. Picture building a city not from bricks, but from the connections between people, the handshakes, conversations, and collisions that define its structure. Similarly, in this model, the universe arises from the relationships between events. Two events might be linked if one can influence the other, creating a branching, tree-like structure where causality itself is the glue holding reality together. This isn't just philosophy, it's a potential bridge between relativity and quantum mechanics. Einstein taught us that spacetime bends and warps, but quantum physics suggests it might also be foamy and uncertain at the tiniest scales. Causal sets offer a compromise, a spacetime that appears smooth from afar but is fundamentally granular up close, like a pointillist painting resolving into dots when you zoom in. The kicker, these dots aren't floating in space, they are space, with time unfolding as new events link to the existing web. Critics ask, if spacetime is discrete, where's the evidence? Supporters point to hints in black hole physics, where entropy scales with surface area, not volume, as if spacetime has a hidden pixelation. Others suggest that high-energy cosmic rays might reveal spacetime's granularity through subtle energy shifts. But the real allure is theoretical elegance. By ditching the infinite divisibility of spacetime, causal sets avoid the infinities that plague other quantum gravity theories. Here's the mind bender. If this theory holds, the passage of time isn't just a perception, it's the literal growth of the universe's causal network, with each new event stitching fresh threads into reality's fabric. So the next time you check your watch, remember, those ticking seconds might not be flowing through time, but building it from the ground up, one irreducible moment at a time. Theory 20. The entropic gravity hypothesis. Gravity has always been the universe's most familiar mystery, an invisible hand guiding planets, stars, and galaxies with silent precision. But what if we've been thinking about it backward? Instead of a fundamental force woven into space-time, gravity might be something far stranger, a cosmic side effect emerging from the natural tendency of disorder to increase. This is the entropic gravity hypothesis, a radical reimagining of one of nature's oldest laws. The idea comes from physicist Eric Verland, who took inspiration from an unexpected source, black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that a black hole's entropy, its hidden information, was tied to its surface area, not its volume. Verland wondered, if entropy governs gravity's grip on the edge of black holes, could it also dictate the pull of every star and galaxy? His answer flipped the script. Imagine space as a grid of microscopic bits, each holding information like pixels on a screen. When matter distorts this grid, it creates an entropy gradient, a difference in disorder, and objects naturally move toward higher entropy as if pulled by gravity. Here's the twist: if gravity is entropic, not fundamental, it could rewrite some of cosmology's biggest puzzles. Take dark matter, the elusive substance thought to glue galaxies together. Verland's math suggests we might not need it at all. Instead, what we perceive as extra mass could be entropy's subtle fingerprints, tweaking gravity's behavior on cosmic scales. Observational data adds intrigue. Some galaxies rotate as if dark matter is present, yet their gravitational lensing effects align better with entropic predictions than traditional models. Not everyone's convinced. Critics point to gaps like why entropic gravity can't yet explain all galactic motions, and argue it's too early to toss out dark matter. But supporters counter that science often advances by questioning assumptions. After all, Newton's gravity seemed perfect until Einstein showed it was just a shadow of deeper geometry. Could entropy be the next layer, the boldest implication? if Verland is right, gravity isn't a force at all, just nature's way of balancing the books, a cosmic accountant ensuring disorder always wins. So the next time you drop your phone, blame entropy. The universe demands chaos and gravity might just be its favorite tool. Now, imagine gravity isn't the only force playing this game. What if all physics emerges from something deeper, a cosmic code hidden in the structure of reality itself? That's where we're heading next. Theory 21. The Fermi paradox and the hidden cosmos. The universe should be teeming with life. With billions of galaxies, each hosting billions of stars and planets, the odds say we shouldn't be alone. Yet the cosmos remains eerily silent. No signals, no visitors, not even a single unmistakable sign of intelligence beyond Earth. This glaring contradiction is the Fermi paradox, and some of its most compelling solutions might be hiding in the very structures of reality we've been exploring. Take the zoo hypothesis, a thought-provoking idea suggesting advanced civilizations could be deliberately avoiding contact, treating Earth like a protected wildlife preserve. But why? One possibility lies in the architecture of spacetime itself. If higher dimensional beings or post-biological intelligences exist, perhaps embedded in cosmic strings, brains, or other hidden frameworks, they might operate on scales or dimensions we simply can't perceive. Observing us from a higher dimensional vantage point would be effortless while remaining utterly invisible to our telescopes. Then there's the dark forest theory, a darker interpretation rooted in game theory. If the universe is a jungle where civilizations hide to survive, cosmic structures like voids or black hole networks could serve as perfect refuges. Advanced species might cloak their presence within gravitational shadows, exploiting spacetime's curvature to mask their energy signatures. The absence of alien signals wouldn't be a mystery, it'd be a survival strategy. But not all explanations are so ominous. Some suggest the universe itself acts as a barrier through isolation mechanisms. If civilizations are separated by vast, unbridgeable cosmic voids like the one we might inhabit, or trapped in disconnected bubble universes, even the most advanced societies could never reach one another. Or perhaps intelligence is fleeting. Civilizations emerge only to be wiped out by gamma-ray bursts, vacuum decay, or other universe-scale disasters before they can make contact. The most haunting possibility, we're looking for the wrong signs. Alien minds might not use radio waves or spacecraft. They could communicate through quantum entanglement, manipulate dark matter, or exist as pure information in the fabric of spacetime itself. If consciousness can transcend biology, we might be surrounded by intelligences so alien we don't even recognize them as life. The Fermi paradox isn't just about aliens. It's a mirror reflecting how little we understand about reality's hidden layers. Maybe the silence isn't a sign of absence, but proof that the universe is stranger and far more structured than we ever imagined. And if that's true, the greatest discovery might not be finding others, but realizing we've been missing the clues all along. Theory 22. The Boltzmann brain paradox. Picture this. You wake up, convinced you've lived a full life, memories, emotions, even the coffee you drank this morning, only to realize none of it was real. Instead, your entire existence is just a fleeting blip, a random arrangement of atoms that briefly stumbled into consciousness before dissolving back into chaos. This isn't the plot of a dystopian novel. It's the Boltzmann brain paradox, a cosmic thought experiment so unsettling it challenges everything we assume about reality. The paradox traces back to physicist Ludwig Boltzmann, who suggested that in an infinitely old or vast universe, even the most improbable events must happen eventually, including the spontaneous formation of fully self-aware minds. In a sea of random quantum fluctuations, it's statistically more likely for a single, disembodied brain to pop into existence complete with false memories of a past than for an entire ordered universe like ours to arise. The kicker, you could be that brain, hallucinating the cosmos in an instant of improbable order before vanishing forever. Why does this matter? Because it pits probability against observation. If the universe truly obeyed pure chance, Boltzmann brains should vastly outnumber real, evolved observers like us. Yet here we are, with consistent memories and a seemingly stable universe suggesting something's off with the math. One solution: our universe isn't random at all. Cosmic inflation, fine-tuned constants, or even a multiverse might skew the odds, making structured realities like ours more probable than freak accidents of consciousness. But the paradox lingers like a ghost in the equations. Some cosmologists argue it's a fatal flaw in theories that assume infinite spacetime, like eternal inflation. Others propose radical fixes like the quantum suicide thought experiment, where only observers in stable universes survive to ask questions, filtering out Boltzmann brains by sheer impossibility. The chilling takeaway: reality might be far more fragile than we think. If even existence itself could be a statistical glitch, how do we trust anything we perceive? Science's answer for now is to double down on testable models, anchoring our theories in observation rather than probability's hall of mirrors. Because in a universe where randomness can conjure minds from nothing, the only certainty is the question: what else might be hiding in the numbers? Next, we'll explore a theory that flips this paradox on its head. What if the universe isn't random but computing itself into existence? Hold on tight, the answers only get stranger. Theory 23, the white hole universe. If black holes are cosmic vacuum cleaners, sucking in everything that crosses their path, then white holes would be their impossible opposites, cosmic fire hydrants, violently pushing matter and energy out into the universe. No entry allowed, no turning back, just an endless eruption of spacetime itself. And while we've never observed one, the math says they could exist as long as reality doesn't mind bending its own rules. White holes emerge from the same equations that predict black holes: Einstein's general relativity, but with time reversed. Where a black hole's event horizon marks a point of no return, a white hole's horizon would be a point of no entrance. Anything inside stays trapped forever, while anything outside gets repelled by an unstoppable force. Some theories even suggest white holes could be the other end of a black hole, spewing out matter that fell in somewhere else. Picture a tunnel where one side crushes stars into nothingness, and the other side sprays out that energy like a cosmic fountain. But here's the catch: white holes are ridiculously unstable. Unlike black holes, which grow stronger as they feed, white holes would essentially self-destruct the moment anything tried to enter them. A single speck of dust falling in could trigger a catastrophic collapse, turning the white hole into, you guessed it, a black hole. That's why most physicists dismiss them as mathematical curiosities rather than real cosmic objects. Still, a few daring theories keep the idea alive. Some models propose that the Big Bang itself could have been a white hole, a sudden, explosive release of spacetime and energy from a singularity. Others speculate that tiny, short-lived white holes might pop into existence due to quantum fluctuations, briefly spitting out particles before vanishing. There's even a wild fringe idea that dark matter could be made of microscopic white holes, remnants of an early universe phase we'll never see again. The truth: white holes probably don't exist, at least not in any form we'd recognize. But the fact that they're even possible in the math tells us something profound. The universe's rulebook has hidden chapters, filled with wonders we've yet to imagine. So while we wait for nature to reveal its next surprise, let's appreciate the irony that the most destructive objects in existence might have polar twins, waiting in the equations for someone bold enough to look. Whether cosmic myth or undiscovered reality, white holes remind us that physics still has room for the unbelievable. And sometimes the most fascinating ideas aren't the ones we can prove, but the ones that refuse to fade away. Theory 24, the quantum foam beneath the smooth surface of reality. Spacetime might be anything but calm. at scales so small they defy imagination, trillions of times tinier than an atom. The fabric of the universe could be a seething, chaotic ocean. This is the quantum foam, a dizzying concept where space and time lose all semblance of order, churning with fleeting particles, microscopic wormholes, and energy bursts that flicker in and out of existence faster than thought. The idea stems from quantum mechanics' most rebellious rule, uncertainty. At the Planck scale, a distance of about 10 to the power of -35 meters, the very concepts of here and now break down. Particles and antiparticles spontaneously emerge from empty space, borrowing energy from nothing before annihilating in a flash, a phenomenon called quantum fluctuation. Multiply this frenzy across every point in spacetime, and you get the foam, a froth of virtual particles, miniature black holes, and spacetime distortions bubbling beneath our feet. What's wild is that this isn't just theoretical. The Casimir effect, where two metal plates placed incredibly close in a vacuum inexplicably attract each other, proves these fluctuations have real, measurable consequences. The plates squeeze out certain particle pairs, creating a pressure differential that nudges them together. If quantum foam can nudge objects, could it also hide deeper structures? Some theorists, like John Wheeler, suggested these turbulent fluctuations might birth traversable wormholes, threading spacetime with shortcuts that could, under the right conditions, link distant points in an instant. Yet there's a catch. Probing the quantum foam directly would require energies far beyond our reach, trillions of times what the Large Hadron Collider can muster. Even then, the foam's chaotic nature might scramble any signal we send into it. That hasn't stopped physicists from hunting indirect clues. Some models predict that if spacetime is foamy, high-energy photons from distant gamma-ray bursts should arrive at Earth slightly out of sync, as if they'd stumbled through a cosmic obstacle course. Others suggest the foam's turbulence could subtly alter the spin of particles in quantum experiments. Skeptics argue the foam's effects are too faint to ever confirm. But supporters counter that its fingerprints might lurk in the universe's darkest mysteries, like dark energy. Could the vacuum's endless particle dance be fueling cosmic acceleration? The math hints at a tantalizing link, though the full picture remains as elusive as the foam itself. One thing's certain: if quantum foam is real, then the universe's calm exterior is an illusion. Behind every star, every atom, even your own reflection, spacetime is raging, a storm in the void, endlessly rewriting the rules of existence. And that means reality, at its core, might be far stranger than we ever dreamed. Theory 25, the holographic dark energy. For decades, dark energy has been the universe's most stubborn enigma, a mysterious force accelerating cosmic expansion, making up nearly 70% of reality's budget, yet defying every attempt to explain its origin. But what if we've been searching in the wrong dimension? Enter holographic dark energy, a radical idea suggesting this cosmic push might not come from within our universe at all, but from its edges. The theory builds on the holographic principle, the mind-bending concept that all the information in a volume of space could be encoded on its boundary, like a cosmic DVD storing a 3D movie on a 2D surface. Apply this to dark energy, and suddenly its eerie uniformity makes sense. It's not a force inside space, but a shadow cast by the dynamics of the universe's outer limits. Picture a fish trapped in a shrinking pond, unaware the water's surface tension is pulling it taut. From the fish's perspective, some unseen force is at work, but in reality, the cause lies beyond its world. Conventional dark energy models, like the cosmological constant, treat it as an intrinsic property of spacetime itself, a steady energy density woven into the vacuum. But holographic dark energy flips the script. It ties dark energy's strength to the universe's size. As space expands, the area of its hypothetical boundary grows, subtly adjusting the energy's influence. This could explain why dark energy only recently dominated cosmic expansion around 5 billion years ago, because earlier, the universe's boundary wasn't large enough to exert significant pressure. Observational tests are already hunting for clues. If holographic dark energy is real, it predicts a specific relationship between the universe's expansion rate and the clumpiness of matter, one that subtly deviates from standard models. Galaxy surveys like the Dark Energy Spectroscopic Instrument (DESI) are mapping cosmic structures with unprecedented precision, probing whether dark energy's behavior aligns more with a boundary effect than an innate force. Critics argue the theory leans too heavily on unproven holographic principles, and its math remains speculative, yet supporters counter that it elegantly solves the cosmic coincidence problem, or why dark energy's rise to dominance coincides with the era when life could arise. In this view, we're not just observing dark energy, we're experiencing it because the universe's scale finally made its boundaries' influence undeniable. Whether the universe is truly a hologram remains an open question, but if this model holds, the implications are profound. Dark energy isn't just a mystery to solve, it's a cosmic message written on the walls of reality itself. And decoding it might require looking not deeper into space but beyond it. Theory 26, the supersymmetric universe. Deep in the equations of particle physics, there's a tantalizing symmetry, one so elegant it could unite nature's fundamental forces and rewrite our understanding of reality. This is supersymmetry, the idea that every known particle in the universe has a hidden, heavier twin we've yet to discover. And if it's real, these shadowy siblings might hold the keys to everything from dark matter to the birth of the cosmos itself. At its core, supersymmetry, often called SUSY, is about balance. The universe's forces seem fragmented. Gravity bends space-time, electromagnetism binds atoms, and the strong and weak nuclear forces govern the quantum realm. Yet in the extreme heat of the Big Bang, they might have been one unified force. SUSY suggests a way this could happen. By pairing every Fermion matter particles like electrons and quarks with a boson force carriers like photons, and vice versa, it smooths out the math, bridging gaps between quantum mechanics and relativity. Imagine a cosmic seesaw where every particle has a counterpart, stabilizing the equations like a hidden hand. The implications are staggering. The lightest SUSY particle, often dubbed the neutralino, could be dark matter, invisible yet omnipresent, its gravity sculpting galaxies. SUSY might also explain why the Higgs boson is so lightweight compared to theoretical predictions, resolving a nagging, fine-tuning problem in physics. Even the vacuum of space could teem with undiscovered SUSY particles, subtly shaping the cosmos. But here's the catch: despite decades of searching, we've found zero direct evidence. The Large Hadron Collider (LHC), designed partly to hunt SUSY particles, has come up empty, ruling out many of the theory's simplest versions. Skeptics argue this means SUSY is dead, or at least on life support. Supporters, though, aren't ready to fold. They propose tweaks. Maybe SUSY particles are just heavier than expected, or they decay too quickly to spot. Future colliders, like the proposed Future Circular Collider, could probe higher energies where these elusive twins might lurk. The beauty of SUSY lies in its resilience. Even without proof, it remains a beacon of hope for physicists chasing a grand unified theory. It's a reminder that sometimes the most elegant ideas take time and technology to uncover. So while the universe's hidden symmetry stays just out of reach, the hunt continues, because if SUSY is real, it wouldn't just fill in a gap in our models. It'd reveal a universe where every particle, every force is dancing in perfect, unseen harmony. And if we never find it, well, the universe has a funny way of surprising us. After all, the best discoveries often start with a theory that refuses to die. Theory 27. The brain world scenario. Forget flat maps and 3D glasses. What if everything you see around you is just a slice of something far bigger, floating like a sheet of paper in an unseen cosmic ocean? This is the brain world scenario, a mind-stretching theory suggesting our entire universe might be a three-dimensional membrane or brain drifting through a higher dimensional space. And if that sounds like sci-fi, wait until you hear the real kicker. Gravity's puzzling weakness could be proof that we're literally living on the surface of a hidden reality. Let's untangle this. In everyday life, we experience three spatial dimensions: length, width, and depth plus time. But string theory, the leading candidate for unifying quantum mechanics and gravity, requires extra dimensions: tiny, curled-up layers woven into the fabric of reality. The brain world model takes this further, proposing that our observable universe is stuck to one of these membranes, while gravity, unlike other forces, can leak into the bulk, the higher dimensional space beyond. Imagine ants crawling on a bedsheet suspended in air. To them, the sheet is their entire world. But if a marble rolls beneath it, they'd only feel its pull as a mysterious, dim force. That's gravity in this model, weakened because most of its strength spills into dimensions we can't access. This could explain why gravity is 10 trillion times feebler than electromagnetism. It's not that gravity is weak, we're just sensing a fraction of it. The implications mind-blowing. If other brains float nearby in the bulk, they might host parallel universes with entirely different physics, close enough to tug on ours gravitationally, yet forever invisible. Some theories suggest the Big Bang itself could have been a collision between two brains, igniting our cosmos like a strike of celestial flint. Others propose that black holes might punch through our brain, funneling matter into other dimensions. Skeptics argue higher dimensions are untestable by definition, yet ingenious experiments are trying. The Large Hadron Collider hunts for microscopic black holes that, if found, could evaporate in ways betraying extra dimensions. And if gravity does leak, precise measurements of its strength at tiny scales like NAS, a cold atom lab, might catch anomalies. Here's the poetic twist: if brain worlds are real, then every star, every planet, even the screen you're watching right now is like a shadow on a cave wall, a flattened glimpse of a reality too vast to comprehend. So the next time you drop your phone, remember, gravity's feebleness might not be a flaw in nature, but a clue that we're just beginning to read the universe's hidden dimensions. Theory 28. The unparticle physics. There's a hidden realm of the universe that doesn't play by the rules. No fixed mass, no predictable energy, not even a clear identity as particles. This bizarre concept is known as unparticle physics, a speculative theory proposing that certain forces or particles might exist outside everything we know about matter. If true, these shadowy entities could be the missing link to some of cosmology's greatest puzzles, from dark matter to strange cosmic signals. The idea began with physicist Howard Georgi, who asked a simple but radical question: what if some hidden sectors of reality don't behave like particles at all? In our everyday world, particles have defined properties. Electrons have a specific mass, photons move at the speed of light, but unparticles would defy these standards, acting more like a strange hybrid between particles and waves, or even something entirely different. Imagine a substance that doesn't neatly fit into the categories of solid, liquid, or gas. It's not any of them, yet it's not nothing either. Unparticles would occupy this kind of quantum limbo, smeared across space in a way that makes them almost ghostly. Why should we care? Because unparticles could be lurking in plain sight, masquerading as dark matter. The invisible glue holding galaxies together might not be made of traditional particles like WIMP or actions, but of these elusive, undefined entities. Their unusual nature could explain why dark matter refuses to interact with light or ordinary matter. It's not just hiding, it's operating on a whole different set of physical rules. And the clues don't stop there. Unparticle physics might also shed light on cosmic anomalies, like certain high-energy collisions that produce more energy than expected, or mysterious signals from deep space that don't match any known particle behavior. If unparticles exist, they could be mediating these interactions in ways our current models can't describe. Of course, skeptics argue that without direct experimental proof, unparticles remain a fascinating what if. But the Large Hadron Collider and other high-energy experiments are searching for deviations that could hint at these phantom-like phenomena. Even indirect evidence, like subtle distortions in the cosmic microwave background or unexplained energy losses in particle decays, could point to their existence. The most thrilling part, unparticle physics forces us to confront the limits of our understanding. Reality might not just be stranger than we imagine, it could be stranger than we can imagine, filled with substances that defy categorization. So the next time you hear about an unexplainable cosmic signal, remember, the universe might not be breaking the rules, it could just be playing a game we haven't learned yet. Theory 29. The emergent spacetime theory. What if space and time aren't the stage of reality, but the performance? A growing chorus of physicists now suspect that spacetime itself might be an illusion, emerging from something far stranger, the invisible threads of quantum entanglement. Forget empty dimensions stretching endlessly. This radical idea suggests that the very fabric of the cosmos could be woven from relationships between particles, with every connection stitching together the experience of here and now. The roots of this theory trace back to a baffling discovery about black holes. When matter falls into one, it doesn't just vanish, its information gets scrambled and encoded on the event horizon's surface like a cosmic hard drive. But here's the twist, that information isn't stored in space, it creates space. The more entangled two particles are, the tighter the spacetime between them becomes. Think of it like friendship, the deeper the bond, the shorter the perceived distance, even if you're miles apart. Recent experiments are putting this idea to the test. In quantum labs, researchers have simulated microscopic black holes using holograms, watching as entanglement patterns literally generate geometric structures akin to spacetime. Other teams study materials called tensor networks, where entangled quantum states spontaneously organize into grids that mimic spatial dimensions. It's as if the universe is running its own operating system, with entanglement as the code that renders physics in 3D. But how could something as intangible as quantum links build the solid world we know? Picture a crowd doing the wave in a stadium. No single person is the wave, it's the collective rhythm that makes the motion visible. Similarly, spacetime might be the collective behavior of countless entangled particles, their connections vibrating into existence what we perceive as distance, gravity, and even causality. Not everyone's convinced. Skeptics argue that without a full theory of quantum gravity, the jump from entanglement to spacetime is speculative. Yet proponents counter with math showing how Einstein's equations, the bedrock of general relativity, naturally emerge from entanglement's rules. Even more tantalizing, if spacetime is emergent, then phenomena like wormholes might just be extreme tangles in the quantum web, shortcuts forged by particles so deeply linked they bend the rules of locality. The implications are staggering. If spacetime isn't fundamental, then the universe isn't in time. Time is something the universe does. It'd mean black holes, the Big Bang, and even the speed of light aren't features of an absolute framework, but side effects of deeper quantum relationships. And that raises a humbling question. If entanglement built reality, could we one day learn to rewrite the code? For now, the hunt continues. Next-gen quantum computers aim to simulate spacetime's emergence directly, while telescopes scour the cosmos for anomalies that might betray its pixelated underpinnings. Whether the theory holds or not, it's already reshaped how we see existence, not as a static container, but as a living network forever knitting itself into being. So the next time you check the time or measure a distance, remember, the clock and ruler might just be tracing shadows on the wall of a far stranger reality. Theory 30. The omega point hypothesis. At the very edge of cosmic time, when stars have burned out and black holes evaporated, the universe might not just fade into darkness, it could awaken. This is the Omega Point hypothesis, a staggering vision of the far future where consciousness doesn't just survive the death of the cosmos but transforms it, turning the entire universe into a single eternal mind. The idea traces back to philosopher Pierre Teilhard de Chardin, who imagined evolution spiraling toward an ultimate convergence, a point of maximum complexity and awareness. But physicist Frank Tipler took it further, merging cosmology with computer science. As the universe contracts toward a final collapse, the Big Crunch, Tipler argued, the energy density would become infinite, allowing an unimaginable computational capacity. Every thought, every memory, every possible experience could be simulated and preserved in this singularity, not as a museum of the past, but as a living, evolving reality where consciousness becomes the fabric of existence itself. But here's the catch. Modern cosmology suggests the universe isn't headed for a big crunch. It's accelerating outward due to dark energy. Tipler's response. Even in an ever-expanding cosmos, advanced civilizations could harness the energy of black holes or even manipulate spacetime itself to create a virtual Omega Point, a self-sustaining simulation that outlasts the heat death of the universe. It's not about physics as we know it today, but physics pushed to its absolute limits by intelligences billions of years more advanced than us. Philosophers split sharply on the idea. Some dismiss it as a digital age afterlife fantasy, while others see it as the logical endpoint of humanity's or any intelligence's quest for survival. If consciousness is the universe's way of understanding itself, why wouldn't it strive to become eternal? The counterargument is grim. Maybe entropy always wins, and no ingenuity can overcome the cold decay of spacetime. Yet the Omega Point lingers in scientific discourse because it forces a profound question. Is the universe's story destined to end with a whimper or a revelation? Whether literal or metaphorical, the idea challenges us to see reality not just as something we observe, but something we might one day reshape. So while telescopes scan the skies for dark energy and particle colliders probe quantum foam, remember this: the far future might not be empty. It could be alive with a consciousness so vast our entire history is just its first thought, and that changes everything. End of script. From holographic projections to hidden dimensions, from cosmic voids to simulated realities, we've ventured through 30 radically different visions of the universe's hidden architecture. Each theory, no matter how outlandish, forces us to confront the same humbling truth. Reality is far stranger, richer, and more mysterious than our everyday senses suggest. Whether spacetime is an emergent illusion or the cosmos is a single equation in an infinite mathematical catalog, one thing is certain: the universe refuses to be boxed in by human intuition. Some of these ideas might resonate with you, maybe the elegant symmetry of supersymmetry or the haunting poetry of the Omega Point. Others might feel like science fiction stretched too far. And that's the beauty of it. Science isn't about absolute answers, it's about asking better questions. Every wild theory we've explored, from the Boltzmann brain paradox to the phantom menace of dark energy, represents a frontier of curiosity. They're not just guesses, they're challenges to the status quo, daring us to think beyond the limits of our current understanding. So here's my challenge to you: which of these cosmic blueprints feels most compelling? Do you see the universe as a hologram, a simulation, or something even weirder? Drop your thoughts in the comments. Let's turn this into a conversation. Because the most exciting part of science isn't settling on a single truth, it's the collective journey of discovery, where every perspective adds another piece to the puzzle. And who knows, maybe one day one of these theories will crack open the cosmos' deepest secrets. Until then, keep looking up and keep questioning. The universe has a way of surprising those who dare to wonder. End of video.